Hi, my name is Federico, a postdoc and association member of ML4Q, and you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computing cluster answer questions about their work in the cluster, their research, and the future of quantum. In today's episode, I'm talking to Kathrin Dorn, a PhD student in the group of Reinhold Egger at the University of Düsseldorf. We will talk about her PhD project and how she started off to combine maths, physics, and arts in her studies and ended up analyzing theoretical aspects of topological insulators. So, hi Kathrin, nice to have you here.
Hi Federico, it's a pleasure.
Also for me. Let's start by understanding how you got to the field of physics and where it all started.
So after finishing high school, I really didn't know what to do. I knew what I was good at. It was arts and maths and physics, and I looked for something in between. So either being arts or a mixture, because there was like architecture or something like this, and also more mathematical things. And then there was this open day at university, and they presented different fields of studying, and in the mathematical and science department we had maths, physics, and medical physics. And it was medical physics which really caught me, because, and that's maybe quite a thing when you finish school, you really want to know what you want to be in the end. And medical physics gave me some outlook. It was being a medical physicist, for instance, in the hospital, and treating patients in oncology. And this was where it all basically started, with studying physics in general.
I see. So I understand it was a bit more reassuring to know what you're going to be after your studies, and maybe that's why also you chose medical physics. You were a bit more sure of what you were going to be. I see. And said, how did you then get introduced to the field of condensed matter?
There was a quite long, or at least not a straight journey to condensed matter physics. In my bachelor thesis, I had to get a better understanding of semiconductors. And at that point, medical physicists didn't really get into touch with semiconductors, except for a small lecture where we just got an understanding of source and drain, so to say. That was the point where I really had to teach myself how this thing works. And besides that, I also attended the master lecture already, semiconductor physics or semiconductor devices. And at that point, I realized I'm quite very interested in this case. And so the next semester I already intended theoretical solid-state physics. And that was the point, I think, where I really switched to theoretical physics in general. And still being a medical physicist, I did my master thesis in theoretical physics, and then I switched.
I see. So basically you were a medical physicist both in your bachelor and master's, but the master thesis was not about medical physics.
Right.
I understand.
But so I actually was allowed to do that because having the master, we have basically, as a medical physicist, you have the basic studies complete for a physicist and beyond, of course, but you have all the basic courses you need. Yeah. And so I was allowed to do a theoretical master thesis.
I see. And after that, you chose for your PhD to continue in this field.
Yes, so it was quite when I was doing my master thesis. ask around the master students if we want to stay, and it took me quite some time to decide this, because it's a time you take for yourself to be a PhD student, and you never know if your project works. And then I decided, since this group is also so nice and helpful, that I want to be a PhD student here.
Mm-hmm. I see. And so, who was your supervisor of your PhD studies?
Reinhard Egger. So it's is the professor of our institute.
Okay. And how did you, or when did you join the ML4Q cluster?
I think it was last year when our student Matthias finished. Then I was the next in line and was joining the ML4Q cluster, and since then I've also attended the conferences and some courses. So
did you enjoy your time so far?
Yes, it was quite interesting, especially in February, where we had this online conference. Even though it was online, especially in the end, we had some very nice chatting together with Professor Ando and Christian Dickel, and some other PhD students like Johannes Kölzer, who also did the first podcast. And yeah.
I see. So I wanted to ask you, since you had this sort of unconventional trajectory towards this field of theoretical physics, I wanted to ask you if you think that your previous experience in medical physics, where maybe you studied more applied things, was anyhow useful for your future, so your future studies, which were instead much more theoretical.
So
maybe as an approach, not necessarily as real knowledge.
Yeah, so when it comes to real knowledge, it's really medical physics is basically it's nuclear physics. So it's in that case, I mean, there are quite some fields that are connecting. For instance, if you look at detector physics, which you need for positron-electron tomography, you have some connection between semiconductor physics, for instance. But it's not the case that you really have some topics that are related to what we do here. Yeah. However, during the medical physics studies, I learned also some things like programming skills and numerical skills, and which were quite helpful in the end. So this is what I really can say. I took it, and in this case, I would say yes. But of course, it's not quite a related topic, and still, it brought me at some point to theoretical physics. So there must be a connection, and I think this was really in that small part of semiconductor physics.
I see. And you already have some definitive plans for your future after your PhD?
Not quite yet, but it's there are a lot of fields which are interesting in case it has to be mathematical. So from my experience from student jobs, I know that that doing just software development to make a software complete for a user is not the mathematical approach I need. So I really do very, very mathematical things, and also analytically. So it's not only numerically with programming. It's really computing things in my head, and it's I need it.
With the pen? So you still use the pen a lot?
I use the pen a lot. So it's really I think that's also what I need.
Yeah. Yeah, I have to say I also use it, and maybe future generations will feel more comfortable writing on a tablet than us. I don't know, but I think we grew up also in school always using the pen, doing math and stuff like that, and I also feel more comfortable with that, right?
Yeah, I like it. I also switched a bit, but I think it's not the same feeling for me as you say. It's quite if you get used to that pen and paper, it's really difficult to get loose of that, and it's quite a thing of creating stuff on that sheet. It's maybe something you get used to.
Yeah. So I heard that you're quite an expert on topological insulators. So do you want to tell us a little bit of what are these things? Because I don't think that many people actually know about them.
Yeah, as a PhD student, you usually have a focus on one thing, and in my case, it's a topological insulator. And a topological insulator is an insulator, or better to say, an insulator with conducting surface. So you have the bulk states being gapped and one gapped surface state. And that's what that's what makes it quite different to the normal insulator. I
see. And do you feel like maybe explaining just in simple terms what is maybe the basic mechanism that allows for such materials to have this behavior?
The crystal structure allows for time reversal invariant points. And if we look, for instance, at a two-dimensional topological insulator, it's quite similar to the quantum spin Hall effect. And where you have applied external magnetic field, and you get those time Z2 topological invariants. But in a 3D topological insulator, it's quite different. You have weak and strong topological insulators, and the weak ones can be produced by stacking layers of 2D topological insulators, while the strong ones can be produced by other materials like chalcogenides, bismuth, and telluride and selenide. And these materials allow for 4 topological invariants. And these 4 topological invariants don't need a magnetic field. And instead, spin momentum locking protects, and spin orbit coupling protects those 4 states. And with an odd number of Kramers degenerate pairs, we have 2 Dirac cones at the end. And these 2 Dirac cones are then, so one of the Dirac cones is a conducting surface state. So you don't need a magnetic field, instead spin momentum locking.
Yeah, so I understand that, this is one of the main differences from this standard quantum Hall effect, that there you need strong magnetic field to create such an effect, external, and here instead it's not needed.
Yes, so you really don't, you really have this 3D topological insulator without an external magnetic field, just because of protected states that you have.
I see. And why recently there is so much attention from the, of course, physics community in topological insulators? So why do you think there is such a big interest in studying them?
So for once, you have this interesting topological structure. So you have a gap, which you can, a closed gap, which you can produce by bismuth alloys and enhancing them with other material, like in this. So first it was done with antimonium, and by adding antimonium at some point for a certain concentration gave you this interesting state. And the other case is so topological insulators have this one surface state which allows for different applications. So you can really, with magnetic fields in the 3D topological insulator, also steer them open or closed. And of course, it's different to a normal insulator. So you have really closed single band gaps. I
see. And you have this conductivity on the surface.
Yes.
And did you study so far more like two-dimensional topological insulators or three-dimensional topological? Because you mentioned there are two types.
I was studying 3D topological insulators, so with bulk insulator. And in my first project, which was based on research done by my supervisor already, was that we had a bulk insulating surface Hamiltonian for the case of a non-wire made out of a 3D topological insulator, and based on that we studied phonon-induced backscattering in the topological insulator.
Yes, and what was one of the things you focused on in your paper? I believe you wanted also to understand how the conductivity on this insulator depended on the temperature.
Yes, exactly. So we wanted to study phases. So we looked at different phases for zero temperature, and found that we also have a spin density wave on the one hand, and we have also a superconducting phase. And the other thing was that we looked at temperature effects for shifted magnetic fields and how phonon scattering, because at a magnetic flux of 1/2, this band gap in a wire is closed. And that's due to the nanowire geometry, because we said we don't need a magnetic field before in order to get a conducting surface state in the 3D topological insulator. But we need that due to the nanowire geometry. So we need a half integer flux to get the gap closed. And having this closed gap, we don't have really phonon effects that interfere. And at a shifted magnetic field, then phonon effects, so especially backscattering for a nanowire on a substrate, which cannot move up or downwards, just longitudinal movement of phonons, we have temperature effects, so we can see it.
I see. And so I understand that your paper is theoretical and you could predict quite a few things about these topological insulators. So is there so far any experimental confirmation of the findings that you had?
Before we worked on this paper, there was already a publication by the group of Weiss in Regensburg. And they studied mercury telluride nanowire. Better to say a strained mercury telluride nanowire, because mercury telluride in general is a 2D topological insulator. Strained mercury telluride is a 3D topological insulator. And so we could compare with their results, and they also showed this the conductivity based on, or better to say, the closed band gap studies for a wire or a nano ribbon, better to say. And so we could quite compare our results with theirs in this case.
And how did they compare?
So we found those conductance steps that we also had, and the conductance steps were basically the results without where phonon interaction didn't really have large impact, and also as already said, we had also numerical studies and looked at the band gap. And this, of course, already coincided with the old research of my supervisor.
It's very nice. I think when one has a theoretical work, like you do a theoretical work, and there is a matching with like experimental evidence, I think it's very nice, especially on such a hard topic like this one. I looked at your paper, and it's full of, as you mentioned, the analytical calculations, and it looks really complicated. So being able to reproduce experimental evidence after all these calculations, it should feel satisfactory, or not?
Yeah, so in this case it was opposite. The experiment was before, but of course it's good if you see, okay, we agree with each other, and you have the feeling at that point we are really we have proven it now from both sides. So
exactly. No, I think this is very important because we know there are fields in physics ongoing where other theoreticians do a lot of calculations, very complicated results, but they don't have the chance right now, and who knows when, to actually verify that what they calculated is somehow describing an aspect of reality of our universe. Because there are also studies where they investigate other type of universes, and it might be still useful in the far future, but maybe I think this can give a bit more of satisfaction feeling, I think, for a theoretician if you have the response of the experiment as well.
Yeah, I talked to Dagmar, and she exactly explained this problem when she said it's we are not in the we don't have the experience now to look at quantum cryptography, and that's of course in my case it's one must say that in case of topological insulators. They have been found around, so predicted around 2005 and 2007, and a bit later they were also really shown experimentally. So it's quite still a new research field, but this experimental investigation really enhanced the whole studies on that point, because we can really show everything. And
it's true. And let's be honest, experimental investigations require funds, but they also bring funds if they are successful, right?
Yeah.
They have usually, at least from my experience, I see that the experimental results, even confirmations, have often a bigger impact maybe than, I don't know, the work that predicted that result. Yes, but both are important, absolutely. I'm also a theoretician, but I absolutely admire the work of the experimentalist. I wanted to ask you maybe a simpler question. So before you were mentioning examples of 3D topological insulators, and it sounded that these examples are all made in the lab, basically artificial. But do you think that these kind of materials can exist in nature already? Can we find them?
So we can really etch, not etch, but we can really vaporize topological insulators. And the really nice thing about bismuth telluride and selenide is that it's even working at room temperature. So it's quite an advantage, and I think this makes it quite so interesting in general.
Yes. So, and what about maybe other applications for topological insulators, like topological quantum computing that requires Majorana fermions? So can one generate these kind of quasi-particles and achieve this?
So that's basically the work we are doing in the cluster. We are trying to do this, and there is work theoretically and experimentally going on in trying to really, for instance, produce those topological devices. So what is done what is known until now is you can put a topological insulator, for instance, as a nanowire. You can put it on a substrate, which is superconducting, and then the whole topological insulator will be superconducting. And according to this, there are predictions, and the research is still going on. That's why it's quite still a very interesting and recent topic to achieve the Majorana fermions, and it's quite difficult to really
to be sure.
And that's why it's really still ongoing topic.
Yeah. Well, I believe that with all these efforts, including the ones in the cluster, maybe we'll get there with more confidence near in the future. Let's hope.
let's hope.
And how do you feel in general about the field that you're working on right now, so topological insulators, in the bigger picture, like in terms of the interest that the community has in it? Do you think it's going to be long-term because of the applications? Or do you think that it might be a bubble that deflates after the most important results are obtained? Do you have a perspective on that?
I think so. So for now, as long as we are, as various fields open, like for instance, looking for qubits, looking for superconducting material, I think as long as we are working on that, it's quite still a recent topic. Maybe. So I think for now it still has a very interesting future. So. But of course, the first great experience was when they were shown experimentally, which of course just raised a new
open, basically.
It was quite a new research field, even if although they were already predicted, and of course direct fermions existed, and Majorana fermions were also already studied, but at that point, I think it was.
Well, at least it took, from what you said, it took not long from the theoretical prediction to the observation, right? It's not like the Higgs boson that I don't know, we had 40, 50 years or so.
Yes. So it was. The time was quite short of predicting it, but of course, with having Dirac fermions studied, it's 1928 and predicting
much later. So the prediction was late, not the observation was early. I see. And do you see some connection in the work that you carried out with maybe the other objectives of the cluster, or the work that is going on in the other groups?
So, as I already said, of course, the AndoLab has applications, experimental investigations on topological devices, and also in groups like, for instance, Alexander Eitland or Achim Roche, they are also studying topological insulators or topological materials. So, in general, it's for sure still a very theoretically very much studied field. Experimentally, of course, as well, but maybe not much that much. So
there's room also there for more work. I see. Well, thank you for this these insights and the work that you did so far, and maybe now. To be a bit more chilled and relaxed, we could play a very easy game. So basically, here I'm going to say 2 words, and you have to choose one of them, no? And quite quickly, so that you shouldn't have time to think, okay? But don't worry, it's nothing difficult. So the first 2 would be intuition or rigor, like being rigorous.
Intuition.
Okay, so is this also your approach when you work?
No, not in science.
Not in
science, it's research.
Okay. The other thing would be art or history?
Art.
Wine or beer?
Definitely wine, but also not that much.
Okay. Cold weather or hot weather?
That's difficult. Can I make a superposition out of it?
So you like both?
Yeah, in both, and it can also switch. So like at the same day.
I see. What about new language or new skill?
Ooh, that's difficult.
If you have to choose, if you're
quickly, then it's maybe a new skill, because so also during Corona I teach myself. So I had some very basic sewing skills, but I teach myself to sew. So it's but I also like to learn new languages. So
that's good. And what about self-learning or being taught?
So self-learning as being a PhD student, of course. But was amazing lectures. So let's say self-learning, but
you also enjoy being taught.
Yes.
Okay, and painting or reading?
Painting.
So do you spend much more time painting than reading?
Yes.
Probably outside your work time.
Outside my work time, of course. Yeah, in my work I don't paint that much, and
we don't want to say that Kathrin most of the time paints and few moments during the day works. Okay. And regarding the conferences, since now we experience both types, you prefer the online ones or the one in person?
I prefer the one in person, to be honest, because whenever I see my students, it's like if they don't understand something, they have the look of they didn't get it. Yeah. And that's the point where I really know I have to repeat this. And especially when it comes to difficult things like entropy, for instance, and you really have to explain entropy a few times to give an understanding what really entropy means in this case. And so I think it's really the lectures in person.
Okay. And coffee or tea?
Tea.
Tea? But you had a coffee before.
No, I didn't have a coffee.
Okay. I thought you did.
I had a tea this morning.
Okay. So you're a tea person.
Yeah.
And final one is very relaxed because about holidays. So you prefer holidays in the countryside or in a city?
In the countryside or beach, if possible. Right now during pandemic, it's always a bit difficult. But
I was going to ask, in fact, the next one is mountains or beach?
It's beach.
Okay, so we know where we can find you this summer then on holidays.
Yeah, if the pandemic, of course, allows it. Yeah, and so...
Okay, well, thank you for the nice conversation, and I hope that also our listeners and viewers had a good time. See you next time. Bye-bye.
Thank you very much.